In this lecture, we shall consider few extensions of Euler-Lagrange equation that we have developed earlier. In Euler-Lagrange equation or in calculus of variation, we started from the extremization problem of the functional, the integral j, which depends on the value of y, where y is involved within another functional dx from x1 to x2. To shorten the notation, we will write it as f of y prime x dx 1 to 2. Instead of writing x1 and x2, we will write it 1 and 2. And we see that the first variation we obtain from this that delta j is equal to 0 implies that we have an equation of this form: del f del y prime minus del f del y is equal to 0, the Euler-Lagrange equation. Here we have considered the function. Now f is a function of independent variable x and the dependent variable y and its derivative with respect to x. Sometimes it may sure happen that the functional f may depend on higher order derivatives, as for example higher order derivatives. So we want to consider the extension of Euler-Lagrange equation when the functional depends on higher order derivatives. Say it depends on y prime, y double prime, and x. So now our problem will be the extremization of the functional y prime, y double prime, x dx. We define a variation like this. We define the alpha dependent integral like this: f of y, capital Y prime, capital Y double prime, and x dx, where we define y as a function of x alpha, which is y of x plus alpha times eta of x, where eta is a function of continuous function of x, such that eta at x1 is equal to 0 is equal to eta at x2. Similarly, y prime, capital Y prime is y prime plus alpha eta prime, and we also use that eta prime at x1 is equal to 0 and eta prime at x2 is 0, and y double prime is similarly y double prime plus alpha eta double prime. So if we consider this function and we say that dj d alpha, then this is, we have del f del y del alpha plus del f del capital Y prime del y prime del alpha, del f del y double prime del y double prime del alpha dx, and we say that this with alpha is equal to 0. So first write it. This is the integral from 1 to 2. So this is integral 1 to 2 we have del f del y, this is eta, this part is eta prime, del f del y prime eta prime, and this part is del f del y double prime eta double prime dx. Now we say that the value of the integral, this value where alpha is equal to 0 is the optimum value or extremized value, and with alpha is equal to 0 we get dj d alpha, when alpha is equal to 0 this gives you in which case, as we said, alpha is equal to 0, the capital Y, Y prime and Y double prime reduces to small y prime, small y double prime respectively. So the quantity becomes del f del y eta plus del f del y prime eta prime plus del f del y double prime eta double prime dx is equal to 0. Now we consider this integration of the second term. The integration of the second term is del f del y prime eta prime dx from 1 to 2. We consider this is the first function, so eta del f del y prime within limits 1 to 2, which is 0 as per this condition, minus integration dx of del f del y prime and integration eta dx 1 to 2. So we get it as 1 to 2 del f del y eta minus dx of del f del y prime eta. And now coming to the second term, we have before the second term integration 1 to 2 del f del y double prime eta double prime dx. We again consider this is the first function, so this is eta prime del f del y double prime within limits 1 to 2 minus eta prime dx of del f del y double prime dx from limit 1 to 2. This is 0 as for this first condition. So we have minus eta prime dx of del f del y double prime dx from limit 1 to 2. Again, we expand, we integrate first, so it is eta dx of del f del y double prime minus there is minus, another minus from the second part, integration by plus, so we have d2 dx to del f del y double prime eta dx from 1 to 2. This is again 0, so the contribution of the second term is d2 dx to del f del y double prime eta dx is equal to 0. So the quantity within the first bracket is 0 because this integral is 0 for all etas which satisfies these conditions. So we see that when the functional contains higher derivative, as we have considered that the functional depends on the second derivative, then the Euler-Lagrange equation becomes Euler-Lagrange equation for such a functional Euler-Lagrange equation becomes del of del y minus dx of del f del y prime plus d2 dx2 del f del y double prime is equal to 0, which can easily be generalized. We consider this is the zeroth term, this is the first term, and this is the second term. So the generalization is like that. K is equal to 0 to n when the function contains up to n derivative. We can write the sign is minus 1 to the power k dk dxk del f del yk is equal to 0, where yk is the k derivative, that is del 2y del xk. This is known as Ostrogradowski equation. Ostrogradowski's equation, which is the generalization of Euler-Lagrange equation when the functional depends on the higher derivative. Still, here we have considered the function to be a single independent variable x. Now we consider a case when the functional depends on two dependent variables. So the functional f depends on two independent variables y and z, but on single single variable, independent variable x. So our functional here is more than one dependent variables. As for example, we choose the independent variable to be y and z, and still this is the second extension of Euler-Lagrange equation. So we consider the functional as y prime, z prime, and x. This is a functional which depends on two dependent variables. Here we define y as y which depends on alpha, and so this is y plus alpha eta of x, and similarly y prime is small y prime alpha eta prime, and for z we write capital Z is equal to small z plus alpha xi, and z prime is equal to small z prime plus alpha xi prime, with the condition that eta at x1 is equal to 0 is equal to eta at x2, and here the xi at x1 is equal to 0 is equal to xi at x2. So we define a parameter dependent functional as integration from 1 to 2 f of y capital Y prime z prime and x dx, and as usual we say that dj d alpha at alpha is equal to 0 is 0, and if we differentiate it we get 1 to 2 del f del y del alpha plus del f del y prime del alpha del f del z del alpha plus del f del z prime del alpha dx from 1 to 2. Del y del alpha is eta is 1 to 2. This is del f del capital Y eta. For this it is del f del capital Y prime eta prime. For this is del f del capital Z xi plus del f del xi prime at Z del capital Z prime xi prime dx. Now for alpha is equal to 0, capital Y reduces to corresponding small y and capital Z reduces to corresponding small z. So we get integration 1 to 2 del f del y eta plus del f del y prime eta prime plus del f del z xi plus del f del z prime psi prime dx is equal to 0. This is the variational part. Now we recall that this part becomes minus ddx of del f del y prime eta when we integrate it in parts and use this condition, and this part reduces to minus ddx of del f del z prime xi when we use this condition. So the equation becomes this condition becomes integration 1 to 2 del f del y minus dx of del f del y prime multiplied by eta plus del f del z minus dx of del f del z prime xi dx is equal to 0. This condition is valid for every eta and xi satisfying the endpoint condition. So the conclusion is that this must be 0 separately and this must also be 0 separately. So when the functional depends on more than one dependent variable, the Euler-Lagrange equation gets decoupled into one equation for each dependent variable. So that here the condition is del f del y minus dx of del f del y prime is equal to 0 and del f del z minus dx of del f del z prime is equal to 0. This condition, this equation we have already used extensively in the case of Lagrangian formalism, when the Lagrangian L depends on Q1, Q2 up to Qn, Q1 dot, Q2 dot up to Qn dot, and on time t. Then for each of these dependent variable we get one equation, that is we get del L del Q1 minus del L del Q1 dot, dt of del L del Q1 dot is equal to 0 for 2, 3 of there were n such independent equation. This is the theory behind it. Now we go to the another extension, that is when the functional depends on more than one independent variable. So this is a very interesting case that we haven't encountered till now. This is the third extension. F depends on more than one independent variables. So we consider if the functional f which depends on single dependent variable which we call z and z prime, and it depends on x and y. So these are the dependent variables, and these are two independent variables. So the optimization condition or the functional is defined as if z, z prime, x, y, dx, dy. This is the double integral. Integration over x and integration over y with limits x1, y1 to x2, y2. Now, this z prime needs to be specified. This depends on del z del x, del z del y, and then independent variable x and y. So we need a change. So this is a functional z del z del x, del z del y, x and y, dx dy. We make a shorthand notation. We write it from 1 to 2. Note that this is a double integration from x1 y1 to x2 y2. We write it f of z, zx, zy, x and y dx. By zx we mean that this is del z del x, and by del zy we mean del z del y. So there are two independent variables x and y. We introduce as before a parameter z, with parameter alpha, so that we write z, which is a function of alpha x y, as z as a function of x y plus alpha eta is a function of x y. Here the eta has the property, eta function has the property that eta x1 by 1 is equal to 0 at eta x2 y2. So this function is 0 at the end points. So if we write zu, that is del z, del ux, that is del z, del capital Z, del x. This is del small z, del x plus alpha times del eta del x. So we write it as zx plus alpha eta x, where eta x is the partial derivative of eta with respect to x, and we write zy is equal to del z del y. This is similarly zy plus alpha eta y. So these are the derivatives. So we define the alpha dependent functional as double integration from 1 to 2 f of z, zx, zy, xy, dx. Now dj d alpha is we integrate from 1 to 2. So this is del f, del z, del z, del alpha plus del f, del zx, del zx, del alpha plus del f, del zy, del zy, del alpha dx dy. Now you see that del z del alpha is del z del alpha. This gives you del z del alpha is equal to, this doesn't depend on alpha, so this is simply eta of xy. So we get it as integration from 1 to 2. This is del f del capital Z times eta. This part is del f del zx, and when we differentiate it with respect to alpha, we get eta x, and for SARS, the next term we have del f del z y eta y dx dy. If we set alpha is equal to 0, this for alpha is equal to 0, this equation becomes integration from 1 to 2 del f del small z eta plus del f del zx eta x. Eta x means del eta del x plus del f del z y del eta del y dx dy is equal to 0. When we integrate this part partially with respect to x, so that is, if we consider this part, del f del zx del eta del x, only considering the integration by parts with respect to x. So first term is eta del f del zx within limit 1 to 2 minus integration eta ddx of del f del zx dx, and there is again y integration over. And similarly the second term, this term del f del zy del eta del y dy is eta del f del zy between 1 to 2. Here limit is what? X1 to x, x1 y1 x2 y2, and then so this is 1 to 2 eta dy del f del z y dy. So the condition becomes, this becomes integration 1 to 2 del f del z minus this part becomes ddx of del f del zx minus del dy del f del zy dx dy is equal to 0. So the Euler-Lagrange equation in this case, this part is 0. So the Euler-Lagrange equation for such case, the Euler-Lagrange equation is del f del z minus ddx of del f del zx minus dy del f del zy is equal to 0. In this notation, when we have a Euler-Lagrange equation in single variable, this is del f del y minus ddx of del f del yx. This is the change in Euler-Lagrange equation. So we have considered three different versions or extension of Euler-Lagrange equation. Firstly, we have considered that there is a single independent variable x and a dependent variable y, but the functional depends on higher derivatives of y, and we got the Ostrogradowski equation. Then we consider the functional which depends on a single independent variable x, but on more than one dependent variable, and we get the Euler-Lagrange equation for each of the independent variables. Finally, we consider the f which depends on more than one independent variable. In this case, there is only one equation. The independent variables are x and y, and dependent variable is z, and we have considered that the functional depends on the partial derivative of z with respect to x and y. So this is the Euler-Lagrange equation when f depends on more than one independent variable. So these are the different variations of Euler-Lagrange equation generally one encounters with.